So when we think about igneous rocks, we really are thinking about magmas. So magmas, some people refer to it as molten rock, but it's not rock yet. It's actually just a body of ions, and those ions eventually are going to form minerals, and those minerals form them in a systematic way. So minerals are formed in a systematic way out of a magma in igneous rocks, and so that's what we're going to discuss today. So we're going to talk a little bit more scientific sort of things now, and not so much the travel log that goes along with igneous rocks. So what you see here in this image, in fact, is new rock forming even as, well, when this photograph was taken. So there's a skim on the outside of minerals that have formed to form, in this case, a rock type called basalt. And in fact, that's a special variety of basalt called pahoehoe. And so pahoehoe is the Hawaiian name for ropey sort of basalt. And so basalt, or basalt as they say in Britain, is a type of mafic rock. It's rich with iron, it's rich with magnesium. It's the sort of rock that forms most of the ocean crust around the entire world. And so basalt is one of those sort of rocks. And so mafic rocks in general form the ocean crust of the world, really. Not so much the continents. So the continents have a little bit of basalt on them, but not so much as what the oceans have. So that is basalt forming in front of your eyes here, kind of. You can see that it was molten and red hot, but as it begins to slowly cool, and that's about 1200 degrees C, or maybe up to 1400 degrees C in some of these basaltic magmas like this. But when they cool, those bonds form and they form certain minerals. And so that's what we're going to talk about today. We're going to talk about the silicate minerals that form from this. If we were to just take the top 10 elements that are in the Earth's crust, you would find that oxygen is number one. That's the number one element in the Earth's crust. And the number two element is silicon. And those two elements alone account for 84% of the Earth's crust. And so 84% of the Earth's crust is made out of silica and oxygen. So it's not surprising, in fact, that most rock-forming minerals that are igneous tend to be silicate minerals. And so we're gonna look at that. And so we're going to combine some of the other elements that are just after that. For instance, aluminum, 8%, iron, 5%, calcium, 3.6%, sodium, 2.8%. Those are the sort of things that are going to bond with the silica tetrahedra. And those are going to form our igneous rocks. And so we also get potassium, of course. With potassium feldspar, we get magnesium. Magnesium, iron-rich and magnesium-rich rocks form basalt, for instance. And then titanium and hydrogen. Hydrogen's the last one on the list here for the top 10, and there's not much hydrogen compared to everything else that's on there. So know that oxygen and silicon are the most important elements in Earth's crust, and they form the bulk of the silicate minerals that form igneous rocks. Yeah, kind of important that way. As we talked about last time, there are intrusive igneous rocks, those that are plutonic, those that form and cool inside of the Earth. And then there are also those that are erupted at the Earth's surface, and we call those extrusive rocks, or they're also volcanic in origin. We're actually going to deal with volcanoes specifically later on in here, but we're going to talk about these differences for right now. And both varieties have to come from what we call a magma. So how do you form a magma? You heat up rocks. You heat them up so much that they melt. And so when they melt, they form a magma. So that's what a magma really is. It is molten material that formerly was rock. And so you melt it. How do you melt it? Well, you turn the heat up. How does that happen? Well, you can do it in various locations in the Earth's crust. You can do it way down low in the Earth's crust where there's a zone of partial melting. And actually in the upper part of the mantle even, you can actually melt rocks there. And so when you melt those rocks, we do it in two ways. You can turn the heat up, or you can also reduce the pressure. If you reduce the pressure, it gives those ions more room to move around and makes it easier for the ions to dissociate, break the bonds, and then melt. And so that's how you do it. You can either increase the temperature or you decrease the pressure, and it's going to go to liquid if you decrease the pressure. So Next on the list here, this actually shows you that I call it a three-sided pyramid. It's actually got four sides because it's called a tetrahedron, right? But there's a bottom here, and then three sides up here, right? So there's 1, 2, 3, 1, 2, and 3, and a bottom down here. That makes four sides. And that sort of structure, it's called a tetrahedron. It has four sides. And make a cool tent design, probably. I often thought that I would do a five-sided tent at some point and design a five-sided tent, call it a pentatent, if you will. It's not copyrighted, so you could probably, register that or something, and make $1 million off of me somehow. Kind of doubt that, though. But here is a tetrahedron. So a tetrahedron make a cool tent, too, if you think about it that way. So there's a peak to it, and there's the three corners, and then there's the bottom to it, right? So that's the tetrahedron. And so in this case, the silicon is right in the middle of that tent. And surrounding it at those 4 points are the oxygens. And so it's SiO4. That's the silica tetrahedron. The oxygens have a -2. The silicon has a +4. And so there's still an unbalanced charge in there. And so what happens very commonly is silicon tetrahedra will attract one another and polymerize long chains or various structures. Alternatively to that, they will bond with things that have a +2 charge. And so you could grab on to either iron or magnesium, something like that, and satisfy that electrostatic imbalance. And so in this case, you've got the silica tetrahedron, just a single tetrahedron here, but it makes it easy to link up with something else. And so that SiO4 has a net -4 charge on it. And so you have 1 or 2 ions that will come in then to attach to it, or you'll get more silica tetrahedra that will attach to it. Now, for the simplest mineral of all is one that links up with the metal ions directly onto that silica tetrahedra, and that would be like olivine. Olivine is MgFeSiO4, or it could be Mg2SiO4, and so that's going to satisfy those -4 charges. You'll have 2 magnesiums that are +2 each that are going to satisfy the imbalance in that silica tetrahedra that way. So that is the structure of olivine. It's a single tetrahedron. It's the simplest silicate mineral you can form from a magma. And when it forms, it's not liquid anymore, right? It becomes a solid when it becomes a mineral. And then it's going to be heavier than the materials around it. And so very commonly you form that olivine crystal or that olivine, ions will bond, and then you form more of them, and then and then they all begin to sink then to the bottom of that magma chamber. And so that is a silica tetrahedron right here. And it is bonding in this case, if we have a single one, to form olivine. If olivine's the simplest one that can form, that's going to be at the highest temperature. In other words, in order to form the other silicate minerals, we're going to have to cool that magma some more in order to get longer sorts of structures out of it. Single tetrahedra, olivine. We can also link up and form chains out of these silica. And that's going to satisfy at least part of that -4 charge. And so if the metal ions can attach and make it possible to link up, so can you form the silica with itself, and it forms a chain. So in this case, you can see a single chain. As it turns out, the minerals that form that way, that's the pyroxenes. Pyroxenes form single chains. And so pyroxenes will also have iron and magnesium attached to it, but not as much as what you get in olivine, because it doesn't have the imbalance that way, because the tetrahedra line up. It's like Legos. You can keep linking them together and you form bigger and bigger structures. Well, that's the way silicate minerals form as well. They polymerize. In other words, they will actually bond with themselves in order to form these very elaborate sort of structures. Starts with a single tetrahedra, goes to a chain after that. So that's the pyroxene. So olivine forms at the highest temperature, pyroxene at a slightly lower temperature where it can link up more structure to it and not break apart from the heat. The heat has a tendency to break things apart. Or, you pull the pressure off, lower the pressure, and it allows things to break apart again and break those bonds. But as we're cooling things, or if we pressurize it, we're going to be able to link these things together. And so that's our single chain is the next one in the list. After that, you can get a double chain. So you can have one chain that attaches to another chain, and you have even more of those minus charges satisfied in the silica structure. And then, therefore, you have to have less of the cations to attach to those structures. And so if we go from a single tetrahedra, we can go to a chain, a single chain. And then next we go to a double chain. And then after that, you can go to a sheet. And show a sheet you can think of as several double chains attached to one another. And so you can see from that, in our original molecule, in the original olivine structure, the single tetrahedra, our ratio was 1:4, 1 oxygen to 4 silica. In the single chain, when you add up all the oxygens and you add up all of the silica in there, that ratio drops. And so it becomes like 1:3 or, even less than that, I think. In a double chain, it's going to be even less. And in a sheet, it's going to be even a smaller ratio. Like, I don't think it's 3:8. 3:8 is what you get with many of the feldspars. So it's not important for you to know, but just know that you can get a sheet structure out of that. And that's going to make some sense. So if we have olivine, which is a single tetrahedra, if we have a single chain that is a pyroxene, like augite, and if we have a double chain that's like hornblende or the amphiboles, we can also have the sheet structures, which are like biotite. So biotite is an example of a sheet structure. And that makes a lot of sense now because that's where the bonds are easy to break, right? They break in these flat sheets. And that's because they form a sheet-like structure. And so that's the crystalline form for all the micas. So it's the same thing with muscovite. In fact, there's a whole variety of these things. So if that is the progression, if we go from a single tetrahedra at the highest temperature, and then a single chain, single tetrahedra, single chain, double chain, sheet structure, and then we go into the three-dimensional sort of forms, and that's going to be like the feldspars. So the feldspars are a three-dimensional structure, and quartz, the most complex of all of the structures. And so the next image is a lot like what I was just telling you, but it's a different illustration just to show you another way to think about it. So here you can see a single tetrahedra at the top. You can see a single chain after that. That's the pyroxenes. Then you see the double chain. That's the amphiboles. That's like hornblende. And then you can see the sheet structure. That's the micas, but also the clay minerals are that way as well. So kaolinite is one of those you're going to see when we get to sedimentary rocks. And then finally, you get down here to the quartz and the feldspars, and that's the complex three-dimensional structures here. So if olivine forms at 1200 degrees, the other ones form at less than that. And so the very last silicate mineral that would form out of a magma, the very last one, is quartz. And quartz forms at the lowest temperature that way, and it gives it more time to bond into that three-dimensional sort of structure that's just a mishmash of silica tetrahedra, but all of the charges, are not, it's not going out looking for metal ions to attach to. Now, it just has all its silica surrounding it, and so that's what satisfies those charges. And so silica, for quartz, it forms around 750 degrees centigrade. Okay, so that's pretty hot still, right? And 1200 degrees centigrade is pretty hot for olivine as well. Now, I think that the magmas at Kilauea volcano, where you get the basalts like that, those are like 1400 degrees when they come out of the ground. Super hot, 1400 degrees Celsius, and so it has to cool a couple hundred degrees before it finally begins to form that basalt there. And of course, it forms basalt first, right? Which is got to be olivine, it's got to be pyroxene, and I don't even think you get any amphibole out of that, actually. So you may get a little bit, but not much. And so that's the type of rock that you would get with basalts, those really high temperature sorts of eruptions like that. And they would be in a magma that's really kind of not very rich with any of the other minerals that you would expect, any of the other elements that you might expect in continental rocks. And so continental rocks have a tendency to form what we call felsic rocks, which would be rich with quartz and rich with feldspar. So that's the general way in which minerals crystallize out of a magma. Now, that's not an original thought with me or with any other geologist that's alive anymore. It was from a guy's brain, his name was Bowen. And so Bowen came up with this thing, and he called it the Bowen's reaction series. It was a very probable explanation for why we get different rock types in the oceans, in the continents, and in fact, in different places, in different tectonic settings around the world. In oceans, we tend to have what we call mafic rocks. And mafic rocks are the rocks that would be erupting in the ocean floor and forming new ocean crust. And that occurs along the spreading centers, which are in a tectonic sort of sense now. That's the area where new crustal material is being added to the oceans in places like Iceland. Iceland has new crustal material being added all the time. The rock there is basalt, and basalt is ocean crustal material. Now, that's made out of olivine and pyroxene, so that's the stuff that crystallizes at the very top. Well, that's the only magma that's available in the ocean spreading centers. You don't get things that are rich with quartz and rich with feldspar there. You're not going to find rocks like that in that sort of setting. So, as we crystallize these minerals out of a magma, they tend to decrease in temperature, and you form new sets of minerals in time as that magma evolves. We go from high temperature, obviously, and eventually it's going to get to a low temperature. And when we finally get down around 750 degrees C, you're going to start forming quartz. So that's the way it does. It goes boom, olivine, boom, pyroxene, boom. You get the amphiboles, and then you get the biotite, right? And so then after that, finally you get down here to where you're getting some of the potassium feldspars. And then you might even get some muscovite after that. So it's not just straight down the list necessarily. So muscovite has more in common with the biotite, right? But there's still some iron and magnesium ions that are going to attach and make biotite, so it has a darker color that way. So this whole diagram is set up with a color gradient on here. You know, we said that the color is not that important when it was in minerals, but as it turns out in igneous rocks, color is very important because it helps us identify the chemical composition of those rocks. And the rationale for that is if we see green igneous rocks, we know that it's going to be rich with olivine, and maybe pyroxene. If we see black igneous rocks, it's going to be rich with olivine, pyroxene, and amphibole. If we see sort of medium gray rocks, it's going to have plagioclase, feldspar in it, as well as those other minerals. If we have rocks that are light colored then in pink or red, those are going to be the ones that are rich with potassium feldspar and with quartz. That's what you get with the granite, for instance. So as we go down the list here, we have a way that we name these sorts of rocks by color. And so if it's a green rock, it's going to be, and it's composed primarily of olivine, we're going to say that it's an ultramafic rock. So ultra meaning like really super mafic rock, right? Well, olivine is rich with magnesium and iron, and that's where that comes from. Mafic means magnesium and iron, which is ferric, right? So MAFIC is mafic, and so mafic is that composition. That's in basaltic rocks. Ultramafic would be super enriched with magnesium and iron, and that's what you get with olivine. So olivine, pyroxene, amphiboles. So if pyroxene and amphibole and a little bit of olivine go into it, we're going to call those a mafic composition. They call it basaltic in this diagram. I'm going to have another diagram after this to explain this diagram. It's the same diagram, but it's going to compare the temperatures. It's going to give you the same information that this one does, but it's going to use different terms. So instead of basaltic, they're going to call it mafic. Ultramafic makes a lot of sense, right? The intermediate part there, this one's called andesitic. You see that word, andesitic, on the right-hand column here? Andesitic is going to be, that's a type of rock. Andesite is a type of rock that's intermediate in composition. So we're going to call those intermediate mafic rocks. And at the very bottom down here, they say granitic, but in fact, we're going to call that felsic. And so felsic, rich in feldspar, in other words. And so felsic means rich in feldspar. And that's the type of rock that granite is. And so that's why they called it granitic in this diagram. Bowen came up with this idea about how minerals will crystallize in a systematic way as you reduce the temperature. In a discontinuous way, it would go from olivine to pyroxene to amphibole to biotite to the potassium feldspar to muscovite and then to quartz eventually. He has another side over here on the right-hand side where you cool and you actually form different feldspars as well. And so if you see the gray arrow on here, that gray arrow represents the calcium-rich feldspars at the very top up there, which form at a high temperature. So calcium-rich feldspars tend to be black. And if you get into the middle part, they tend to be a medium gray. And that's the variety that you had in your mineral sense. It's called labradorite. And so labradorite is a variety of feldspar as well. And when you can get to the bottom of those plagioclase in that continuous series, in Bowen's reaction series, you get to the bottom down there, you get into the sodium-rich feldspars, the sodium-rich plagioclase feldspars. And the sodium-rich ones, they're going to be white or very, very light colored. And when you finally get into the potassium, which is just below that at the tip of the arrow there, those are the pink ones, pink and tan, light, very light, white color sometimes as well. And so that's the potassium feldspar. Hope that's enough to give you an idea. You're going to want to memorize these charts. So if not this one, memorize the next one, which is a little bit more well done in some ways, but at the same time, I think there's just, it's the same amount of information in either one of these. So you can see olivine, pyroxene, amphibole, biotite next, and then finally in the discontinuous series, then you're going to drop down to the potassium feldspar, the muscovite, and then eventually into the quartz there. And you can see the calcium-rich all the way down to the sodium-rich plagioclase feldspars over on the right-hand side here. So calcium at the top, sodium at the bottom, black at the top, white at the bottom there, and gray and intermediate in the middle part there. So again, there's a lot of terms to memorize here. Let me give you a little bit more background too. And why this is important. It's important because the rocks that are in Earth's mantle, the rocks that are down below Earth's crust, those are predominantly ultramafic. They tend to be made out of olivines and calcium-rich plagioclase and rocks like that, or minerals like that. So that's the ultramafic rocks. That is the mantle's composition. They tend to be greenish, or they tend to be dark, really black in color. So that is what Earth's mantle is made out of. When it comes to the ocean crust, it has that basaltic composition, or it's mafic in composition, like the basalt that you saw on the first slide. That's the composition of what the Earth's oceans are like. So the ocean crust is that color. And so that's going to be the mafic rocks. Next on the list, you get andesitic. And that's where you get a mixture of rocks that are continental and rocks that are oceanic. And you get that where continents override the oceans and you get volcanoes there. Same for the Andes Mountains, in fact. So as South America rides over the East Pacific plate, or they call it the Nazca plate there in the east of the East Pacific Rise, as it rides over the top, that material gets assimilated together with some of the crustal material from the continent, and it forms these intermediate compositions there. And most continents, in fact, are composed of felsic rocks. And you can think about it almost like a distillation process, because the continents are absolutely ancient and the oceans are almost like yesterday on this planet. The oldest ocean crust is only 190 million years old. I say only. That's because the continents are like almost 4 billion years old. Some of them, parts of them are anyway. Really, really old stuff. That's the continents. And so the continents are much older than what the ocean crust is. We're going to get to that when we talk about plate tectonics as well. But it explains the structure of the Earth. And so if the mantle is made out of ultramafic rocks, The oceans are made out of mafic rocks. Some mountains, some volcanoes are made out of andesitic or intermediate volcanic rocks. And then the granitic rocks at the bottom, all those are actually felsic magmas. Now that's what you get like in the Cascade Mountains. And so the Cascade Mountains, famous for their very explosive eruptions there, those are where you would see things like rhyolites or where you would see granites as well. And so those are the sorts of rocks that you get. And so you can see the temperatures vary from 1200 down to 750 degrees centigrade in Bowen's reaction series here. So that's a really important concept to get that. As we go on, here's the summary. Igneous rocks with ultramafic minerals form first. In Bowen's reaction series, the igneous rocks with ultramafic minerals, that is olivine, some of the pyroxenes, they form first, and some of the calcium plagioclase as well. When it comes to the next in the series, the igneous rocks with mafic composition form second. And then the ones with intermediate composition, so biotite, and maybe some of the sodium-rich plagioclases, those are going to form in the middle part. And then the very last, you're going to get the igneous rocks with the felsic composition. So that's going to be things that are really rich in potassium, things that are enriched with silica, the silica tetrahedra. So quartz, for instance, that's all around. It's the last thing that forms, and it's the last one that's going to be preserved in a magma. It's the last mineral to form in a granite, for instance. So in fact, you're not going to find beautiful six-sided quartz crystals in a granite. That doesn't happen very often. Instead, what you get is the quartz, being the last that forms, fills in all the spaces between the other crystals. And so granite has that sort of capacity to look like a sponge, essentially, and the quartz is the last bit of water that fills in the pore spaces. So the temperatures range from 1200 to 750 C. The discontinuous series, once again, I listed here, olivine, pyroxene, amphibole, biotite. For the continuous series, that is in the intermediate through the ultramafic, and that goes from the very highest temperature in the calcium-rich plagioclases all the way down to the sodium-rich plagioclases. So black, all the way through gray, all the way eventually down to the white minerals at the very bottom, then the very lowest temperatures. And so the very lowest temperatures of all then, the felsic minerals would include K-spar, muscovite, and quartz. So that is probably enough for this part of it. That explains magmas and the way that minerals systematically form out of magmas when you either increase the pressure or you decrease the temperature and you get these magmas to begin to crystallize, okay? So that's Bowen's reaction series, probably one of the more important aspects of geology. It's certainly the most important way to explain why we get certain minerals in certain igneous rocks. And so I'm going to break it right here and say that's where we take magmas and we form igneous rocks out of them. We're going to go more into igneous rock identification next. And so how do we identify these rocks? Well, it's all based on the crystal size and the composition, the mineral composition. So what is that color, in other words? So in the mineral size is going to be related to what you can see with the naked eye. And so that is it for Bowen's reaction series. Anyway, I'll take you on to help you identify igneous rocks next.